Welcome! In this video, we'll tackle the problem number 482, license key formatting. This problem involves reformatting a string into a specific pattern, which can be challenging but rewarding to solve. Let's dive into the details and explore efficient solutions together. In this problem, we are tasked with reformatting a string S that represents a license key. The string consists of alphanumeric characters and dashes, where the dashes act as separators between groups of characters. However, these dashes may not be placed correctly, and our goal is to reformat the string so that each group contains exactly k characters. The only exception is the first group, which can contain fewer than k characters but must include at least one character. Additionally, all lowercase letters in the string must be converted to uppercase. The result should be a new formatted string that matches these rules. The input includes the string S, where the length is between 1 and 10 to the power of 5, and an integer k, which can range from 1 to 10 to the power of 4. The output will be the reformatted string. This problem combines tasks such as removing dashes, converting characters to uppercase, and grouping elements, making it a great exercise in string manipulation. Let's look at an example to clarify the problem. Suppose the input string is S equals 5F3Z2E9W and the grouping size k is 4. First, we remove all the dashes from the string, which leaves us with 5F3Z2E9W. Next, we convert all lowercase letters to uppercase, resulting in 5F3Z2E9W. Once that's done, we divide the string into groups of exactly 4 characters, starting from the end of the string. This gives us the groups 5F3Z and 2E9W. Finally, we combine these groups with dashes in between, forming the output 5F3Z2E9W. This process ensures that the license key is formatted correctly according to the rules. Now, consider another example where the input is S equals 2-5G3J and K equals 2. After removing all dashes, the string becomes 25G3J. Then, we convert all lowercase letters to uppercase, resulting in 25G3J. Next, we divide the string into groups of size 2, starting from the end. This gives us the groups 2, 5G, and 3J. Combining these groups with dashes, the formatted string becomes 2-5G3J. Notice how the first group contains only one character, which is allowed as long as it has at least one character. Finally, let's look at an edge case where the input string is S equals and K equals 3. After removing all dashes, the string becomes empty. Since there are no alphanumeric characters left to format, the output is simply an empty string. This highlights the importance of handling edge cases carefully. For instance, if the string contains only dashes, the output will always be empty. Similarly, if k is greater than or equal to the length of the alphanumeric characters in S, the entire string will form a single group. On the other hand, if k equals 1, every character will be separated by a dash. These scenarios help ensure that the solution is robust and handles all possible inputs correctly. To solve the license key formatting problem, we first considered the brute force approach. The intuition here is straightforward. We iterate through the string S, remove all the dashes, and then reformat the characters into groups of size k. The process begins by cleaning up the string, removing all occurrences of the dash, and converting all characters to uppercase for uniformity. After that, we traverse the clean string in reverse order, inserting dashes after every k characters to separate the groups. Once this is done, we reverse the string again to restore the correct order, giving us the final formatted result. While this approach is simple and works within a time complexity of O(n), as we process the string in linear time, it does involve some redundant steps like reversing the string twice, which could be optimized further. The space complexity is also O(n), due to the creation of a new string to store the result. To tackle these inefficiencies, we explored an optimized approach that avoids unnecessary operations. In the optimized approach, we streamline the process by directly building the result string in reverse order, eliminating the need to reverse the string twice. Starting from the end of the string S, we iterate character by character, skipping dashes and counting valid characters. After every k valid characters, we append a dash to separate groups. This ensures that we only add dashes where necessary without any redundant operations. Once the iteration is complete, we convert the result to uppercase before returning it. This approach preserves the O(n) time complexity since we still traverse the string once, but it avoids the extra overhead of reversing the string. The space complexity remains O(n) because we need to store the formatted result. Another method we considered is the modulo arithmetic approach, which involves calculating the size of the first group explicitly. This is useful because the first group may be smaller than k. By removing the dashes up front and converting the string to uppercase, we can calculate the size of the first group as len s%k. After appending the first group, we handle the remaining groups of size k. While effective, this method introduces additional complexity due to the mathematical calculations and edge case handling required, such as when the string length is evenly divisible by k. Given these considerations, we chose the optimized approach as the most balanced strategy for solving the problem. It achieves a good trade-off between clarity and efficiency. The brute force approach, while easy to understand, involves redundant operations like reversing the string twice. On the other hand, while the modulo arithmetic method is efficient, it introduces additional complexity in terms of calculations and code readability. The optimized approach avoids these pitfalls by building the result string in reverse order, which simplifies the logic and reduces unnecessary steps. This keeps the solution efficient in both time and space while remaining intuitive and easy to implement. Some key observations that led us to this decision include recognizing that removing dashes and converting to uppercase are independent pre-processing steps that simplify the problem from the start. Additionally, working from the end of the string allows us to handle group separation without worrying about special cases for the first group being smaller than k. This was an aha moment that significantly simplified the approach. In weighing the trade-offs, we found that each approach has its merits. The brute force method is straightforward and beginner-friendly but slightly less optimal due to the double reversal. The modulo arithmetic method, while efficient, is less intuitive and involves additional complexity in its implementation. The optimized approach, however, strikes the perfect balance. It avoids redundant operations, maintains clarity, and is efficient in terms of both time and space. By adhering to the problem constraints and simplifying the logic, the optimized approach ensures that we achieve a clean and effective solution. In conclusion, this strategy is the best choice for solving the license key formatting problem while balancing performance and simplicity. This problem is all about reformatting a string that contains alphanumeric characters and dashes into a specific grouping pattern. The goal is to divide the string into groups of size k, where each group is separated by a dash, and the entire string is converted to uppercase. The first group can be smaller than k if the total length of the string doesn't divide evenly. We start the algorithm by pre-processing the input string. First, we remove all the dashes to simplify the processing. This can be done using the replace method, which efficiently removes all occurrences of the dash character. Next, we convert all characters to uppercase using the upper method. This ensures uniform formatting and makes it easier to work with the string in subsequent steps. After pre-processing, we calculate the group sizes. The size of the first group is determined by taking the remainder of the string length divided by k, using the modulo operation. If the remainder is 0, the first group will have exactly k characters. Otherwise, it will contain the remainder, which ensures proper alignment for the subsequent groups. The remaining groups will all have exactly k characters. Finally, we construct the formatted output. To do this efficiently, we use a list to store the groups as we create them. Lists are ideal here because they allow us to append elements quickly. We start by extracting the first group from the string and appending it to the list. Then, we process the rest of the string in chunks of size k, appending each chunk to the list until all characters are grouped. Once we have all the groups stored in the list, the final step is to join them together with dashes to form the formatted string. This can be done using Python's join method, which allows us to concatenate all the elements in the list with dash as the separator. This approach ensures that the final output adheres to the required grouping format. There are a few key insights that make this algorithm both efficient and reliable. First, pre-processing the string by removing dashes and converting to uppercase simplifies the problem. It ensures that we're working with a clean and uniform string, which makes subsequent steps straightforward. The modulo operation is another critical part of the solution, as it helps us determine the size of the first group, which may differ from the others. Using string slicing combined with a loop allows us to extract substrings of size k efficiently, ensuring an overall linear time complexity. It's also important to consider edge cases. For instance, if the string doesn't contain any dashes, the algorithm still works correctly because the pre-processing step doesn't depend on their presence. Similarly, if the string's length is less than k, the entire string becomes the first group, and the output is valid. If k is equal to 1, each character becomes its own group, which is also handled naturally by the algorithm. And if the input string is empty, the output is simply an empty string, which aligns with the problem's requirements. The algorithm relies on two primary data structures, strings and lists. Strings are used for the input and intermediate processing, such as removing dashes and converting to uppercase. Lists are used to store the groups of characters before they are joined to form the final result. Lists are ideal for this step because they allow efficient appending of elements as we process chunks of the string. Now, let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the length of the string. This accounts for the operations of removing dashes, converting to uppercase, and slicing the string into groups. Each of these operations processes the string in linear time. The space complexity is also O(n), because we need to store the process string and the groups in a list before joining them. Together, these considerations make the algorithm both time and space efficient. Let's take an example to walk through the solution. Suppose the input string is 2-5G3J and the group size k is 2. We'll apply the algorithm step by step to see how the output is generated. First, we remove the dashes from the input string. This gives us s equals 25G3J. Next, we convert all the characters to uppercase, resulting in s equals 25G3J. Now, we calculate the size of the first group using the modulo operation. The length of s is 5, so len s %k equals 5% 2 equals 1. This means the first group will contain one character. We extract the first group, which is 2, and initialize the result list as result equals 2. For the remaining groups, we process the rest of the string in chunks of size k. The first chunk is 5G, so we append it to the result list, making result equals 2, 5G. The next chunk is 3J, which we also append, resulting in result equals 2, 5G, 3J. Finally, we join all the groups in the result list with dashes to form the formatted output. The result is 2-5G3J. This demonstrates how the algorithm processes the input step by step to produce the correct output in a structured and efficient manner. This Python solution reformats a given string s into a license key format with groups of size k, ensuring all characters are uppercase and separated by dashes. The process begins by removing all dashes from the input string using replace and converting all characters to uppercase, ensuring a consistent format. Next, the size of the first group is determined. This is calculated as the remainder of the length of the clean string divided by k. If the remainder is 0, the first group will have size k. The result is then initialized with this first group of characters. Using a loop, groups of size k are added to the result list by slicing the clean string in steps of k. Each slice corresponds to a group of characters. Finally, the groups in the result list are joined with dashes using dash.join, result, and the formatted string is returned. This ensures the output is in the correct license key format, adhering to all requirements of the problem. The code handles edge cases such as strings with no dashes, strings that are already formatted, or when the input string is empty. The implementation is efficient with O(n) time complexity, where n is the length of the input string, as the string is traversed only a few times for cleaning and grouping operations. Here, we start by defining our solution class and implementing the method license key formatting. The first step is to sanitize the input string. We create a string builder called cleaned and iterate over each character of the input string. If the character is not a dash, we append its uppercase version to cleaned. This ensures that all dashes are removed and the remaining characters are consistently in uppercase. Next, we calculate the size of the first group. This is determined by the remainder of the length of cleaned divided by k. If the remainder is 0, it means the first group size should be equal to k. This calculation ensures that the first group is properly adjusted to accommodate the remaining characters evenly. We then initialize another string builder named result, where we append the first group of characters directly using the substring method on cleaned. This forms the foundation of the formatted key. Next, we handle the remaining groups of characters. Starting from the end of the first group, we iterate through cleaned in steps of k and append each group to the result. To maintain the correct format, a dash is added before appending each subsequent group. This ensures that the groups are evenly spaced and separated by dashes. Finally, once all groups are added, we convert the string builder into a string and return it as the formatted license key. This approach is efficient, as it avoids unnecessary string manipulations and ensures that the formatting process adheres to the problem's requirements. In this example, we start with the input string 5f3z2e9w and the group size k equal to 4. The first step is to remove all the dashes from the input string, which gives us 5f3z2e9w. Next, we convert everything to uppercase to ensure consistency, resulting in 5f3z2e9w. At this point, the cleaned variable holds the value 5f3z2e9w. Then, we determine the size of the first group by calculating the remainder of the length of cleaned, which is 8, divided by k. Since 8% 4 equals 0, the first group size is exactly 4. Finally, we initialize the result by taking the first 4 characters from cleaned, which forms the first group, 5f3z. With the first group determined, the result array now contains the single group 5f3z. The next step is to process the remaining characters in chunks of size k, which is 4 in this case. Starting from index 4, we take the next 4 characters from cleaned, which gives us 2e9w, and we add this to the result array. At this stage, the result now contains 2 groups, 5f3z and 2e9w. Finally, we join these groups together using dashes to create the formatted output string. The result is 5f3z2e9w, which is the desired output for this example. For this second example, the input string is 2-5g-3-j with k set to 2. The first step is to remove all dashes, leaving us with 25g3j. After converting this to uppercase, we get 25g3j. The cleaned variable now holds the value 25g3j. To determine the size of the first group, we calculate 5% 2, which equals 1. This means the first group will consist of just the first character. We then initialize the result array with this first group, which is 2. At this point, the result array contains the first group, 2. Now, we process the remaining characters in chunks of size k, which is 2. Starting at index 1, we take the next 2 characters, which gives us 5g, and add it to the result. Next, from index 3 to 5, we take the final 2 characters, 3j, and add this as well. The result array now contains 3 groups, 2, 5g, and 3j. Finally, we join these groups with dashes to produce the formatted output string 2-5g-3j, which is the result for this example. In the third example, the input string is, and k is 3. The first step is to remove all dashes. Since the string consists entirely of dashes, removing them leaves us with an empty string. Converting this empty string to uppercase results in no change, so the cleaned variable remains empty. With no characters to process, the first group size becomes irrelevant, and we cannot initialize any groups. At this point, the result remains empty. Here, the result array is still empty because the clean string contains no characters. Since there are no groups to process, we skip directly to the final step of joining groups with dashes. However, as the result array is empty, the formatted output string is simply an empty string. This concludes the processing for this example, resulting in an output of an empty string. To analyze the time complexity of the license key formatting function, we begin by looking at the string cleaning process. First, the function removes all dashes using the s.replace dash operation. This requires scanning through the entire input string, which has a length of n, so this step takes n time. Next, the .upper operation converts all characters in the string to uppercase. Similarly, this also involves processing each character in the string, adding another n to the time complexity. Since these two operations are performed one after the other, the total time for cleaning the string is n plus n, which simplifies to n. After cleaning, the algorithm determines the size of the first group by computing the remainder of the string length modulo k, using len, cleaned, %k. This is a simple arithmetic operation that runs in constant time, O1. The conditional operation that follows, or k, also runs in O1. So, the time complexity for determining the first group size is O1. Now, let's consider the process of building the groups. The algorithm uses a loop to iterate over the clean string with a step size of k. Specifically, it runs from the first group size to the end of the string, incrementing by k in each iteration. In the worst case, this loop will execute approximately ceil, len, cleaned, /k, times, which is proportional to O(n/k). Inside the loop, the algorithm slices the string to extract groups of size k using the operation cleaned, I plus k. Since slicing a substring of length k takes O(k) time, the total time for slicing across all iterations is O(n/k*k), which simplifies to O(n). After the groups are built, they are joined together with dashes using the dash.join result operation. The total number of characters in the result, including the clean string and the inserted dashes, is proportional to the length of the clean string, so this operation also runs in O(n). Adding all these steps together, the overall time complexity is O(n) for cleaning the string, O(1) for determining the group size, O(n) for building the groups, and O(n) for joining the groups. Therefore, the total time complexity of the algorithm is O(n). Let's now examine the space complexity. First, the algorithm creates an intermediate string called cleaned by removing dashes and converting characters to uppercase. This requires storing a copy of the input string without dashes, which takes O(n) space. Next, the result list is used to store the formatted groups. In the worst case, the number of groups is ceil, len, cleaned, /k, but since these groups are references to substrings of the clean string, the space required by the list is proportional to O(n). Finally, the output string generated by dash.join result also requires O(n) space to store the formatted result. When we combine the space used for the clean string, the result list, and the final output string, the total space complexity is O(n) plus O(n) plus O(n), which simplifies to O(n). To better understand the efficiency of this approach, let's compare it to a naive solution. A brute force method might involve repeatedly slicing the string, inserting dashes, and converting characters in multiple passes. This would result in redundant operations, potentially leading to a time complexity greater than O(n). In contrast, the optimized approach we are analyzing minimizes redundancy by cleaning the string first and then formatting it in a single pass. This ensures the algorithm maintains both time and space complexities at O(n). Analyzing the best, average, and worst cases further highlights this consistency. In the best case, where all characters are already uppercase and no dashes are present, the algorithm still processes the string in O(n) time. For the average case, with typical input containing a mix of dashes and lowercase characters, the complexity remains O(n), since the string is fully processed in one pass. Even in the worst case, with a very large string containing many dashes and lowercase characters, the algorithm performs the same sequence of operations, keeping the time complexity at O(n). To solidify our understanding, let's consider a mathematical proof of the algorithm's time and space complexities. The dominant operation is processing the input string, which has a length of n. Each major step, cleaning the string, grouping characters, and joining groups, processes the string in linear time or less. There are no nested loops or recursive calls that would result in exponential or quadratic growth. Instead, all operations are directly proportional to the input size. This confirms that the overall time complexity is O(n). Similarly, in terms of space, the algorithm uses a constant number of auxiliary data structures, such as the clean string, the result list, and the output string. Each of these structures is proportional to the size of the input, resulting in an overall space complexity of O(n). This linear scaling makes the solution highly efficient and suitable for processing large inputs. When working on this problem, there are a few common mistakes to watch out for. First, not removing the dashes from the input string before reformatting can cause issues with group sizes and lead to errors during string manipulation. Always ensure the string is cleaned before proceeding. Another frequent error involves handling the last group incorrectly. If the total length of the string isn't a perfect multiple of the group size k, the first group will have fewer characters. It's essential to calculate this properly to avoid misplacing or incorrectly sizing that initial group. Off by one errors in grouping are another pitfall. Remember that the first group should have %k characters, while all subsequent groups should contain exactly k characters. Additionally, watch out for inefficiencies in your string operations. For example, repeatedly concatenating strings inside a loop can be very slow for large inputs. Instead, use a list to build the result and then join it at the end, which is much more efficient. Finally, don't overlook formatting requirements like converting characters to uppercase. If the problem specifies this, skipping that step will lead to incorrect results. Always double-check the problem statement to ensure you've met all requirements. Now, let's discuss some important insights to keep in mind during an interview for this problem. One key skill is recognizing patterns within the problem, such as the need to pre-process the string, like removing dashes, and then applying a structured approach to divide it into groups. Edge cases are another critical area to address. For instance, consider inputs with no dashes, strings shorter than the group size k, or strings with lengths exactly divisible by k. It's important to clarify these scenarios with your interviewer and demonstrate that your solution handles them effectively. In terms of approach, while brute force methods may work, leveraging techniques like string slicing and modular arithmetic can make your code simpler and more readable. Finally, clear communication is vital. Articulate the edge cases you've considered and explain how your solution accounts for them. This conveys your attention to detail and systematic thinking. You might also find it helpful to explore related problems. For example, LeetCode 938 focuses on efficient traversal and pre-processing, while LeetCode 67 emphasizes edge cases in string manipulation. Problems like LeetCode 125, which involve filtering characters, can also offer valuable practice for this type of task. Lastly, let's explore alternative approaches and their trade-offs. The brute force method is often the simplest to implement but can be inefficient for large inputs due to repeated string concatenations. It's fine for small datasets, but it's not optimal when performance matters. A more efficient alternative is the optimized string builder approach. By using a list to collect characters and joining them at the end, you can avoid the inefficiency of repeated concatenations. This keeps the time complexity at O(n), while improving space efficiency. Another option is the two-pointer technique, where you dynamically build groups as you traverse the string. This can be more intuitive for some and avoids multiple iterations of the string. For a less common but interesting approach, recursion can also be used to divide the string into groups. However, recursion is generally harder to debug and can become inefficient for larger inputs. Each of these methods has its strengths and trade-offs, and the right choice often depends on the specific constraints and requirements of the problem. Great job! To wrap up, we reviewed the solution for license key formatting, explored its complexity, and highlighted key takeaways. Remember, consistent practice is crucial for mastering problems like this. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!